Okay, our next topic on the topic of variance is how does the variance change, or how is the variance impacted when we change when we transform the random variable by what's called a change in scale and location. Okay. All right, so we're going to let x and y, we're going to define two random variables, x and y. We have real numbers, constants a and b. And we're going to define y to be a function of x. It's ax plus b. Okay, what does this mean, just to be clear? So remember the definition of random variable. So a random variable is a function from the sample space to the real numbers, right? So, and similarly, so this means that for every sample point, there's some value, some output x of omega. And similarly, y is a random variable, so it takes sample points to real numbers, and we define those real numbers in terms of the values that x takes. Okay. So that's how we define this. So we say that y is obtained from x by a change in scale and location. The scale, to get our terminology straight, is A. The location change is B. Right? So when you scale something, you multiply by a certain value, you either you blow everything up or you shrink everything down. When you add a value, you shift everything over in one direction or the other. So you're changing its location. Okay. So when we change scale and location, first thing is, how our expectation and variance affected by change in scale and location. Okay. Well, let's calculate the expectation of y. What do we know about y? Well, the only thing we know about y is how it relates to x. So it's ax plus b. What can we say about the expectation of ax plus b? Well, we know by the rules, by the linearity of expectation. So this is just the rules of expectation is if we have a random variable and we add a constant to it, that constant can come out. And if we multiply a random variable by a constant, that constant can come out. So it's a times the expectation of x plus b. Okay. So what is okay, so that's nice. So what is y minus the expectation of y? Well, y by definition is ax plus b. The expectation of y is a expectation of x plus b. So we have this quantity here. Okay, so we see that this piece and this piece will cancel. We see that the a can come outside, so what we end up with is a quantity times the expectation times x minus the expectation of x. And so then what does that tell us about the square of the squared deviation, the squared error, y minus its expectation? It's just the square of this piece up here, which is a squared times x minus expectation of x squared. Okay, so what was the point of all of that? Well, the point of all that was to say that, how do we calculate variance? Well, the variance of y, right, by definition, is the expectation of y. It's the mean squared error. It's the expected deviation from the mean. But we've already shown what that is, what that deviation is. This is the expectation of, in terms of x, a squared times x minus the expectation of x squared. Again, by the properties of expectation, if we have a constant, we can pull it out. And here we have a scalar, which is a squared times the expectation of x minus the expectation of x. But that's just the variance of x. A squared times the variance of x. So the key consequence here is that the variance of ax plus b is equal to a squared times the variance of x. The standard deviation of ax plus b is equal to the absolute value of a times standard deviation of x. So that is how variance behaves under changes in scale and location. Okay. So why is that interesting? Well, think about it. If we saw for expectation, first of all, let's record this here. For expectation, if we have a change in scale and location, the expectation changes accordingly, its scale and its location, right? And we saw that here. So if we shift by b, the expectation also shifts by b. If we scale by a, the expectation also scales by a. For variance, though, variance is only affected by the scalar multiple a. It's not affected by a shift. Why? Because, think about it. Suppose this is how the variable varies. So it looks like this, but then we add b. So we add b. This is the regular random variable x. And then this is x plus b. So we shift it over and add b. Well, the expectation has moved accordingly from here to here. So our best guess has shifted over. But once we adjust our best guess, the expected error in that guess stayed the same, right? The variability around that guess hasn't changed. So the variance hasn't changed. The variance changes, however, if I take x and I multiply by, let's say, some value a, which maybe shrinks down concentrates X around the value that it was before. Well, now I've shrunk the variance. And so that can affect, that will affect the variance. Okay. All right. So something to keep in mind are these formulas. Okay. Let's do a quick example into or at least this comes into play quite often in what's called standardization, or expressing a random variable in standard units. So if X has a mean mu and a standard deviation sigma, let's define Z to be X minus the mean divided by the standard deviation. So we're subtracting off the mean, we're dividing by the standard deviation. Then Z, so Z is equal to the number of standard deviations that X is either above or below its mean. And the expectation of Z is 0, and the variance of Z and the standard deviation of Z are both 1. And you can work that as an exercise. Actually, it should be a fairly straightforward exercise using the formulas we have above, because this is a change in scale and location, where the scalar is 1 over sigma and the change in location is minus mu over sigma. Okay, so we can use the formulas up here to calculate mean and standard deviation easily. And using the standardization of a random variable, this comes into play often. Try to normalize to put a random variables on a common scale, or at least an easily interpretable scale. And so we'll see that often throughout the course.